So we are trying to look at question number 42. Now this is an easy question, except the only difficulty is identifying the center of two consecutive rarefactions or compressions. Now I think it's easier to identify the centers of compression first. Like one compression is here, the other compression is like here. So that is like 0.0 to 0.5. This is 0.5, not 0.45. So if you use that value for wavelength, lambda is equal to 0.45 meters, 0.5 meters, then V is equal to F lambda. F is equal to V by lambda 340 by 0.5. That's 680 hertz, right? So that's answer B. If you think that it is not exactly at 0.5 but a bit to the right of 0.5, so if you think that the wavelength is not exactly at 0.5 but slightly off it, that's like 0.52, so 0.52. If you use the value 0.52 for the wavelength, then 340 divided by 0.52 would give 650 hertz. So in the answers given, still 680 is the closest. And even if you use 0.54, still you get 630, still it is the closest. So it is okay even if you are not sure which is the exact position of the center of compression. So will be the case when identifying the center of rarefactions. If you want, you can use the centers of rarefactions and do the question. Again, there will be a range, but still since the answers are very different, it doesn't matter much. Okay, then '52nd question relates to the 42nd question. There's a very better explanation with an animation by another YouTube video, so I have shared it in the playlist. Please take a look at it, you will understand it better. It's difficult to explain this question without an animation, so we watch that video there. And then question number 54. So when a object is moving towards, the frequency increases. So when the object is at this position, it is moving towards the observer, the frequency increases. So when he is moving towards the observer, the frequency increases, and when it is moving away from, so I just want to make sure it's blue shift. When it is moving away from the observer, the frequency decreases. Doppler effect, okay, redshift. And when it is moving perpendicular to the observer, when it is neither moving this way or that way but simply moving, then there is no change in frequency. The observed frequency would be same as the normal frequency, the frequency of the source. So So if you look at this question here, obviously the observed frequency changes between a maximum value and a minimum value, and they could have asked you what is the, like, denote in the graph what is the source frequency. That will be in the middle. Okay, the question is not asking you about the source frequency, but it is asking you what will happen if the rate of rotation increases. So if you haven't read the question, please pause the video and read it. So the rate of rotation of the binary star increases. What is the change of F max and the F change to F minimum? So now the object is moving even faster. So if you look at that Doppler equation, now it is very tempting to use the Doppler equation here. Okay, so you might argue that if observed is equal to the speed of light over, when it is moving towards, it is minus the source speed times F original. It is very tempting to use this equation and to argue that when the rate of rotation increases, this factor increases, so the observed frequency would increase. But the issue is this equation is not applicable for electromagnetic waves. It is applicable for sound waves and some other water waves and some other waves like that, but not for light waves or electromagnetic waves. Doppler effect is observed in them as well, but this equation is not applicable. Since this is an MCQ, even those who have used this equation and have got it still will get the marks. But if it's an explanation, this explanation, if you use the equation, that's incorrect. Though the equation for the Doppler effect of electromagnetic waves is quite similar, still it is not the same equation. So you have to approach this question conceptually. When the star starts moving faster towards the observer, the Doppler effect would increase, so the F maximum would be even greater. And similarly, when the rotation increases, the star would also move away from the observer quickly. So when it comes to this section, it would move away from the observer very quickly. Hence the Doppler effect would also increase, and the F minimum would decrease even further. So F maximum would go even greater, F minimum would decrease even lower. So the answer is C. Then we are going to look at question number 66. So this is similar to that question. So vehicle carries a microwave transmitter. Please read the question. If you haven't read it, pause the video and read it. Now this is normal Doppler effect question, but with a certain difference, that there is not just the object is moving, but it is moving with an acceleration. Okay, so when the object, we know that faster an object is moving towards the source, the shift is going to be even greater, the observed frequency is going to be even greater. So so what is happening here is first it is traveling with constant speeds, and then so when it is traveling with constant speed, the observed frequency is f4. Then it accelerates, then it travels at a higher constant speed, then it decelerates and comes to 0. Okay, so if you look at the velocity time graph, first it is traveling with a constant speed, then it accelerates, the vehicle. So we don't know whether it's constant acceleration or changing acceleration, but it is not going to affect our answer, so I'm just taking it as a constant acceleration. Then it travels with a higher steady speed, then it decelerates to 0. So we have altogether the first steady speed v1 and the second steady speed v2. The observed frequency when the object is traveling with the first steady speed is f4. Okay, so the Doppler effect would increase if the speed of approach increases. The only good news is the vehicle is not traveling backward. It is always moving towards the detector. So here if it is f0, now here it is traveling even faster. So if you look at the frequency, the observed frequency, we don't know what is the original source frequency because we don't know the frequency when the car was still. Okay, so we just know when the car was moving with v1 it has a frequency f0, so it would travel with f0 here in this region, and then the speed increases. When the speed increases, the observed frequency should also increase. Then it will have a higher observed frequency. It will reach a higher observed frequency here, and it will remain at that higher observed frequency. So this will be f0 dash, the higher observed frequency. Then the speed decreases, and when the speed comes to v1, the observed frequency will also come to v1. Observed frequency will also come to the original observed frequency. v1 corresponds to f0 observed frequency. So when the speed comes to v1, the observed frequency would also come back to f0. And when the speed goes to 0, now this is the tricky part. When the speed goes to 0, the observed frequency would come to the frequency of the source, which will be lower than the initial observed frequency, because initially the car was moving and f observed was always greater than the frequency of the source. So the graph would come to the source frequency and it will not go to the 0 value. So if you apply that in that situation, for question number 66, you will have answer C. The observed frequency will rise, then remain steady, then fall to a lower frequency than f0. Okay, so f0 will rise, remain steady, then fall to a lower frequency than f0, and it will fall to the source frequency. Then we're going to look at question number 58 quickly. So if you haven't read the question, read it, pause the video and read it. This is easy. The microphone is moved through 3 centimeters. From 12 centimeters it is moved to 15 centimeters. So it moves from one minimum to another minimum 3 centimeters. That is one node to another node 3 centimeters. That means lambda by 2 is 3 centimeters. So what we have is one minimum to the next successive minimum, one node to the other node. It's actually a standing wave question which accidentally came into this worksheet. So this lambda by 2 is equal to 3 centimeters. This is at 12 centimeter, this is at 15 centimeters, so the distance moved is 3 centimeters. So if you just, then the rest is easy. V is equal to F lambda. If you want, F is equal to V by lambda. So the V is 336 divided by lambda would be 6 centimeters, since lambda by 2 is 3, 10 to the minus 2. This would give you an answer for 58. Answer is C. It will give you 5600 Hertz. Be careful, there is 56 as well, so if you have forgotten to convert the unit, you would end up with 56 and a wrong answer.